Okay, so excellent work everyone on coming in on your holidays when you're doing lots of study, which is good anyway. So my plan today is we've got the 2020 sample exam. It's a 2-hour exam, but my plan is to work through it together with you guys. So I want to sort of talk about some strategies as we're going through it, just talk about how we're thinking about it, and yeah, go through it. And hopefully we can sort of finish it in an hour and a half, hour and 40 minutes. Yeah, that's the plan. And we'll be presenting, I'll bring the graphs up, I'll bring the questions up so I can point to it there, do the solving up here, just work through it together. At the end, happy to catch up, answer any questions you've got, and print anything that you might need and so forth. So that's what we'll do for the first tube, and then if you like this kind of strategy, we can do the same thing for the second tube. Otherwise it can be a drop-in or just get a bit of feedback. All right, so let's get straight into it. We've got the 2020 sample exam. So we've got question 1, find dy on dx for each of the following. There's no need to simplify your answers. Okay, so the first one is y equals x squared e to the x. X squared e to the x. So we're looking at that, and we're going to use the product rule here. We've got one function multiplied by another. So let's be very clear about what's u, what's going to be u dash. X squared and 2x, and v will be e to the x, which means v dash is also e to the x. And then when we combine them together, we have u dash v plus u v dash. And that's all we need to do. We don't need to simplify it. Okay, looking at question B, we have some function to the power of n. We have x plus cos x to the power of 4. All right, so we're going to differentiate that. We have a function to the power of n. We need to use the chain rule. So we can go straight to dy and dx. It's going to be n f of x to the n take 1. N f of x, n take 1, and then multiplied by the derivative of the inside. Cos x goes to negative sin x. Hey Lauren, just grab yourself a booklet there. Oh, yeah. You got one, Sophie? Yep, sure. Last one, we've got y equals ln. We've got x squared plus 3x on top of x. So we're going to use the quotient rule here. We have one function at the top and another function at the bottom. We've got u on top of v. So let's be clear. U is ln of x squared plus 3x. So u dash involves the derivative of an ln function. So that's going to be the derivative of the inside, 2x plus 3, on top of the inside, x squared plus 3x. Alright, so if we have ln of f of x, the derivative is f dash of x on top of f of x. We've got v is x, which means v dash is 1. And we'll combine all of those without simplifying it. So we'll have u dash v quotient rule, u dash v, take away u v dash on top of, the whole thing is on top of v squared, which would be x squared. Okay, so on the first page of your exam, it's not going to be a guarantee, but in the past 20 years, so we've got good inductive evidence to infer, there's going to be some questions about differentiation. So you want to make sure you're getting them right. Okay, we need the differentiation rules, and that's just to get you in the mood, feeling good about what we're performing here, what we're doing. So we've got to make sure we get those questions right. Okay, very good. Let's move on. Question 2 here. We've presented with a graph. We've got the graph of g of x is shown between 0 and 3. Points A and B lie on the curve. Point A is the only point of inflection. Which of the following statements is true? So we're presented with 3 choices. We've got g dash of 1 is less than g dash of 2. So what is it saying? If we're talking about g dash, they're talking about the slope. Remember, if g is the function, g dash is the slope. The slope at point 1 is less than the slope at point 2. That's what the first proposition is saying. The second one says the slope at point 1 is equal to the slope at point 2. So we should look at that. We can see they don't have the same steepness, so we're going to reject that one. And then the last one, the slope at point 1 is greater than the slope at point 2. So just from looking at this, you can sort of see where it's steeper, right? If you're going to trace along with a ruler, where's it going to be steepest? It's going to be steepest at point A, okay? And so that means the third proposition is the correct one, that the slope at 1 is larger than the slope at point 2. Okay, so that's where we're going to put a tick, but we need to provide a justification. So you get 1 mark for the right box, you get another mark for a justification. So the justification is going to be something like, point A is a point of inflection, okay? And we should remember this from calculus. Points of inflection on the function correspond with maximums and minimums on the derivative function. So turning points on the derivative function, which means the slope is maximized or minimized. It's got the highest modulus, the highest size at that point. So that's what we're going to say. Because A is a point of inflection, it has the steepest slope over this interval 0 to 3. Now, if I do go a bit fast, please let me know. And slow down. Clear this up. Alright, so just to restate that rather than writing it up. Point A is a point of inflection, and as such, it's going to have the steepest slope. Alright, that's when the slope is maximized. Okay, move on to part B. Okay, now we've got another 2 propositions. We've got g dash dash of 2 is less than 0, g dash dash of 2 equals 0, and g dash dash. What does the second derivative tell us? The second derivative tells us about 2 things: points of inflection, and it tells us about its concavity, whether it's up or down. So if it's positive at that interval, it's going to be concave up. If it's negative at that interval, it's concave down. And if it equals 0, then we have a point of inflection. Okay, that's what g dash dash of x will tell us. And we're talking about this point, all right, and we can see that is not a point of inflection. Okay, it's not a point of inflection, which means this point is telling us something about the concavity of it. Over this interval, it is concave down. We can see it's opening downwards, which means over this interval, g dash dash of x is less than 0. Okay, if it's less than 0, then it's going to be concave down. So that's the proposition that we need to check. Justification, g of x is concave down at x is 2. Okay, it's concave down at that interval, so the second derivative is going to be negative at that point. Excellent, let's move on. Okay, does anyone remember this question? It's popped up in a practice test for discrete random variables. So, let's have a read of it. We have the owner of a local pet food shop is offering an incentive program to attract customers. The shop owner has placed 50 bowls in a bucket. Each bowl is labelled with a percentage discount that the customer will be given after their purchase is tallied. The customer draws a bowl randomly from the bucket, and the percentage discount of the bowl is applied to the purchase total. The bowl is then placed back in the bucket before the next customer draws a bowl. All right. So that, because we've got replacement, the binomial distribution can apply, the probability is the same. Of the 50 bowls in the bucket, we've got 1 that's got 100% discount, 2 that have 50%, 4 that have 25, 8 that have 20% discount, and the remaining 35 bowls are a 10% discount. So you go along to the shop, and when you go through the checkout, they offer you this bucket with all the bowls in it. Grab a bowl, how much discount do you get? All right, what's the probability that a customer will draw the ball labelled 100% discount? Well, we have one that has 100% out of 50. All right, so that's going to be our answer to part A. 50 balls in total, one of them says 100% discount. All right, we've got 500 customers each draw one bowl from the bucket. What is the probability that more than 10 of these customers will draw the bowl labelled 100% discount? Okay, so if we think of how many customers out of 500 could get a 100% discount, we've got 0, 1, 2. Here we're talking about what, 10, 11, 12, all the way up to 500, okay? You could have 500 customers get the 100% discount, you could have 0. It says, what's the probability that more than 10? So that's the probability of this event occurring, right? Probability of it being more than 10, it's 11 or greater. So what we're saying is, it's a BCD calculation. We're going from 11, okay, 11 people, up to 500 people, out of 500. And what's the probability that they get the 100% discount? 1 out of 50, or 0.02. That's the calculation we're going to perform for this one. All right, now I've always made the argument that you should write this kind of information down, not because it generates marks, okay, in an exam situation it won't, but because in a test it would. I've made that case, but in an exam situation it won't. They're interested in the final answer. Because when you finish the exam and you want to go back and check, you can see what's the thing that I put in my calculator here. All right, so you've sort of written it down, you've saved it. So you're communicating it to yourself. It doesn't take long. All right, has anyone evaluated that before I do?
0.42.
Thank you. 0.42. Okay, let's move on. The shop owner could offer an alternative incentive program in which a 15% discount is offered to all customers. In the long run, which of these two incentive schemes will cost the shop owner more? All right, so we can either offer 15% discount, flat rate, or they can do this activity where they put their hand in the bucket and pull a bowl out. So when you first come across this question, you're like, what am I going to do here? How am I going to do this? And what we should be doing is we should calculate what's the expected discount. Okay, if you think about it, it's a probability distribution. And we have all these events. We have a 10% discount, 20, 25, we've got a 50 and a 100% discount. And all of these have their respective probabilities, right? So here's the events, here's the probabilities of those events occurring. We have 35 out of 50 bowls have a 10% discount. We've got 8 out of 50 have a 20, and we've got 4, 2, and 1. And so we have a probability distribution, and what we can determine from this table is the expected discount. We can calculate E of X, the average result. All right, the average result, the mean, so you can do that two ways. Okay, we can do it by going 10 times that, plus 20 times that, plus 25 times that, and add them all up. Or you can put it in your calculator in a table and have your calculator do it for you. So when you evaluate this one, you get 16.2%. All right, so using the bowl game, where you pull a bowl out of the bucket, the expected discount is 16.2%, or the managers said they can offer a flat rate of 15%. The question is, what's better for the manager? All right, under which scheme are they going to make more money? Well, this one. They're offering less discount to the customers, which means they get to retain more profits. Okay, so you need to state that. It is better for the manager to offer 15% flat rate discount because they will retain more profit. Very good. Okay, let's move on to question 4. All right, we've got the function ln of 3x plus 8. So if you think about, well, firstly it says, for what values of x is f of x defined? So we've got f of x is ln of 3x plus 8. What I want you to remember about logarithmic functions is that ln of x will exist provided x is greater than 0. if you think about their graph, right, it's asymptotic to the y-axis. All right, so it only exists for positive values of x. So if we translate that to this circumstance, this has to be greater than 0. Okay, the inside component has to be greater than 0. So it's going to exist provided 3x plus 8 is greater than 0. Doesn't exist at 0, so we can't say greater than or equal to, we have to say greater than 0. And inequalities operate almost the same as an equal sign. So let's go through and perform it. We're going to have 3x is greater than minus 8. And we'll have x is greater than minus 8 on 3. The only difference with inequalities is when you multiply or divide by a negative number, you flip the inequality. Here we're dividing by a positive, so we don't flip it. All right? Only when we multiply or divide by a negative. Okay, using algebra, solve the equation f of x equals 0. All right, so we want to know when does ln 3x plus 8 equals 0. We're solving for x. What's the x values that make this true? So what we want to do is get rid of the ln, right? How do we get rid of ln? We put e to the power of both sides. All right, e to the power of both sides. We're maintaining equality. And e and ln, they're going to effectively get rid of each other, right? It's a good way to think about it. So we're going to have 3x plus 8 equals e to the power of 0, 1. Any number to the power of 0 is 1. And so then we're going to have 3x is 1 take away 8 minus 7 and divide both sides by 3. Yeah, Colin, it looks like it's just come back on. Like maybe it was taking a while to warm up or something. I don't know. Oh, did you? Yeah, right. I had it turned on for about 20 minutes and nothing was happening. So, yeah. Cool. All right. So we've got x is negative 7 on 3. That's the solution. Evaluate f of 0. So when you put 0 into this equation, so f of 0, we're going to have ln of 3 times 0 plus 8, ln of 8. All right, so there's those 3 parts done. Jump over this page here. On the axes below, sketch the graph of the function, clearly showing all the information. So I'll jump over to Desmos here. We've got ln of 3x plus 8. So the information that we need to show is the root that we found. All right, so the root is this one here, isn't it? Minus 7 on 3, or we've got up here minus 2.3 recurring. And the asymptote, there's a horizontal asymptote, so if I provide a rough sketch of it, we have an asymptote at minus 8 on 3. It has to exist for values greater than that. So I'm going to say that's minus x equals, because it's a vertical line. X is minus 8 on 3. The root is minus 7 on 3. And we've got the y-intercept, f of 0 is ln 8. So I just want you to demonstrate those components. Now ln 8 you can evaluate to a few figures if you want to. 2.079, so that gives you a good indication of where it's going to pass through on the axis you're presented with. Now whenever they give you an axis, okay, so you're putting it in your calculator to graph it, ln 3x plus 8, set the v window to the exact same constraints that they've got. Okay, so you're going from x is minus 5 to positive 5, and y is minus 5 to positive 5. And that's going to tell you exactly where each of the components of the graph should go. Very good. Okay, so then we'll move on to the next one, or the next page. And they're just going to flow on from that, but we just have it presented in a general case. Now consider the function g of x is ln bx plus c. ln of bx plus c, where b is greater than 0 and c is greater than 0. So they're both positive. Find the asymptote, okay? Well, the asymptote occurs when this part equals 0, right? Because the middle there cannot equal 0. So the asymptote is going to occur when bx plus c equals 0. You see how it flows on from what we just did. So that's going to give us bx equals minus c, and x is minus c on top of b. So we don't have numbers there, we're dealing with the abstract case. but they operate the same, don't they? We treat B and C as variables.
Say it has to be greater than.
So that's when it exists. It exists for values greater than that. We're asked what is the equation of the asymptote. So because it's an equation, we have equals. Yeah. So it'd be correct to say this function exists for x is greater than minus c on b, which means the asymptote occurs at minus c on b. All right, good question. Find the coordinates of the x-intercept. Well, the x-intercept occurs when the function equals 0. All right, so we're going to put e to the power of both sides again. So we'll have bx plus c equals 1. We'll have bx equals 1 take c. And then x equals 1 take c on top of b. And then find the slope at x is 0. How steep is it? So this one's a little bit different. So if we have the function, we've got g of x is ln bx plus c. What is g dash of x? That's going to give us the derivative function in which we can put the slope. So to differentiate ln of f of x, it is f dash of x on top of f of x. Okay, f dash of x on top of f of x, that's the derivative function. And we want to know what is the slope when x is 0. G dash of 0 is b on top of, well, that component's going to be 0, b on top of c. Okay. So these stats questions I find annoying just because there's heaps of things to read. But nonetheless, it's important to make sure we read it all properly and thoroughly and don't assume what it says, because that's when you have to backtrack. So we'll read through it carefully. In one particular city, there have been many thefts of student possessions from schools. In an attempt to reduce these thefts, the government has provided new lockable cupboards to all schools in this city. Each student at each school has been assigned a separate cupboard and has been instructed to store their possessions in their cupboard and always keep it locked. All right, so it's just a bit of context to the problem, right? The government conducts a survey of school students to determine how many students always keep their cupboard locked. From a sample of 320 junior secondary students, the following 95% confidence interval for the proportion of junior secondary students who always keep their cupboard locked is calculated. So we've got the confidence interval, 0.9797 is less than p is less than or equal to 0.878. Okay, so based off the confidence interval, somewhere between 79% and 87% of students lock their lock. Explain the meaning of this confidence interval. Okay, so that's what we're going to state. The true proportion and I probably should add something at the start actually. We are 95% confident. Okay, because we've performed the 95% confidence interval. So we're 95% confident that the true proportion lies in this window. All right, so that's going to be what it means. Okay, B part 1. What proportion of the students in this sample always keep their cupboard locked? What's it saying? We've performed a sample of 320 students. What proportion of the sample? What's the observed value of P hat? What was the proportion we observed from the sample of 320? And we're not told it explicitly from the confidence interval, right? Here's the upper boundary, here's the lower boundary. But what we do know is p hat lies exactly halfway between them. Exactly in the middle is going to be the value of p hat. Okay? So a good way to calculate it, we're just going to do the top boundary plus the bottom boundary divided by 2. Alright? So the observed value for a confidence interval always lies exactly halfway in the middle. So, anyone done it? 0.838. Okay, hence, how many of the 320 students in this sample always keep their cupboard locked? Okay, so here's the proportion of students that keep their cupboard locked. Here's how many we sampled. So therefore, 0.838 times 320 is going to tell you how many students in the sample kept their locker locked. What'd you get, Tom? 268 students. Okay, very good. Flip the page over. It is suggested that senior secondary students are less likely than junior students to always keep their cupboard locked. Therefore, the government surveys a sample of 120 senior secondary students and finds that 74 of these students always keep their cupboard locked. So now we're looking at a different group of people. We're not looking at the junior secondary students, we're looking at the senior. Calculate a 95% confidence interval. So, 95% confidence interval for proportion. I'm just going to do this in my calculator. So in statistics, we're going to test Z first sample. So interval Z first sample. All right. Does anyone need those instructions? Interval Z first proportion. Sorry. Interval Z first proportion because we're calculating a proportion. And we're asked 95% confidence, so our C level is going to be 0.95. We've got 74 out of 120. That's the information we're going to put in. That's the value of the confidence interval. We've got between 0.5 to 9. So I'm going to write out 4 figures and then we'll round it. Okay, and I've said with a confidence interval, you can just round normally. 5, that's going to be 30. 704. Okay, so based off this confidence interval, we have between 53% and 70% of senior students locking their locker. Can the government conclude that senior students are less likely than junior students to always keep their cupboard locked? Explain your answer. All right, 2 marks. Yes. All right, because the confidence interval for junior students is completely above the confidence interval for senior students. Okay, so yeah, the lower boundary here does not overlap with the upper boundary here. That's going to be an appropriate answer. All right, yes, because the junior confidence interval is completely above the senior confidence interval. All right. Question 6. We've got y equals x e to the minus x, find dy on dx. So product rule again, we've got u and v. So when you differentiate e to the minus x, you get minus e to the minus x. Smash all that together for dy on dx, u dash v plus uv dash. And so I'm just anticipating, sorry, there's an x there, anticipating the negative, plus uv dash, it's got the negative, so I'll bring it out front. Okay, so that's part A. Part 2, hence show that the integral of x e to the minus x. Okay, show that the integral, I might not write the show that proposition, I might just get straight into the question. It wants us to show that. Alright, so what we know from part 1, okay, anytime there's a hence, anytime you see that, Noah, that means using what you just did, using what you just did. Okay, so what did we just do? We differentiated this and we got this. So therefore, what's an integral statement? The integral of this, all right, integral of e to the minus x, take x, e to the minus x. Okay, the integral of this is going to equal that. Okay, we know if we differentiate that, you get that. Therefore, if you integrate that, you get that. Okay, and we are trying to isolate this component of it. All right, that's what it wants us to solve for. So we can use fundamental theorem of calculus, the properties of it. We can split that integral. So we're going to have integral of e to the minus x, take the integral of x e to the minus x. Okay, and now it's just like some algebra, right? This is the part we're interested in. So I'm going to move this whole component. I'm going to swap the sides. Okay, I'm going to move this one over here and this one over here. So I'm going to take that and take that from both sides. So let's write what we're left with. Now be careful here. The dx is here, right? Integral of that. And then we have take away. And if we've moved this component over this side, alright, so we're trying to solve for that. We've shoved that over, that's here. We've moved this part over here. So we've isolated this component of it, but we're not finished because we need to evaluate this integral. And I said, be careful about that. I should have dx written there because we're just asked to evaluate that component of it, not the whole thing. So when we evaluate the integral of e to the minus x, we'll get minus e to the minus x. And then we need a plus c, right? Okay, and we've verified it, QED. That's what they wanted us to show. All right. Any questions about that one? Very good. So let's move on to the next page then. We have the graph is shown for x e to the minus x. An estimate is required for the area bound by the bound by the function, the x-axis, and the vertical lines x equals. Do you guys have a number written there? No. No, it should be x is 1 and x is 5. Yeah, mine hasn't printed with a number either. I'll just see what it says in here. Yeah, so there's some sort of weird typo thing going on here. Should say x is 1 and x is 5. They've got the box drawn there. Two rectangles, each 2 units wide, have been added to the graph to be used in the calculation. Okay, so here's what we're doing in this part, Sam. Calculate the overestimate by finding the sum of the area of these 2 rectangles to 3 decimal places. Okay. So, the function is x e to the minus x. And we've got rectangles. I might just draw an approximate curve of it. So we've got, here's the first one, and then here's the second one. And we're going from 1, we've got 2, 3, 4, 5. All right. So the width of the rectangles, so we're going to do our upper estimate first. The width of the rectangles is 2. So the first rectangle is going to be 2 times this y value. And what is this y value? All right. The y value here is when x is 1 in this equation. All right. Remember, this is the equation, and we have the x value of 1. We're putting that into the equation. It's going to be 1e to the minus 1. All right, so that's the height of the first rectangle. And then we're going to have plus 2 times the height of the second rectangle. They always have the same width, don't they? And you can factorize the 2 if you want to, it doesn't matter. The height of the second rectangle occurs when x is 3. What's the y value? 3e to the minus 3. Alright. So I'll evaluate that quickly. I mean, what's other ways of presenting it? 2 on e plus 6 on e to the 3. We need it to 3 decimal places. So let's write down 4 decimal places. Don't get that confused with significant figures. Plus. All right, I've got 1.03448. Now we were asked 3 decimal places. So that means 3 figures after the decimal point. All right, so it wants 3 figures after the decimal point, which means we need to round this one. All right, we're not interested in the 8, we need to round the 4, and 4 stays as is, doesn't it? So that's going to be our answer there, 1.034. Okay, a new overestimate of the same area can be calculated using 4 rectangles of equal width. On the graph above, draw 4 rectangles that could be calculated. All right, so we've already got the upper ones drawn, but if we're drawing 4 rectangles, all right, that means they're going to have a width of 1. All right, so we're going to draw these rectangles in, aren't we? So I'll give you a couple of seconds to draw them in. All right, and then we have now calculate this overestimate. Well, the width of the rectangles now, so here's our new overestimate. The width of the rectangles now is 1. All right, so we have 1 times the height. Well, the height of this one is 1e to the 1, plus the height of the second one. All right, the height of this rectangle is x is 2, 2e to the minus 2. And then we have, plus 3e to the minus 3 plus 4e to the minus 4. All right, so the 1 we don't need because we've got one lot of it. But let's put it in there for argument's sake. So let's evaluate this. E to the minus 1. E to the minus 3. All right, I've got 0.8611. Okay, again, 3 decimal places. So they want those 3 figures, and this one stays as is again. So 0.861. That's 3 decimal places. Very good. Okay, part C. With reference to A part 2, find the area bounded by the x-axis and the vertical lines between x is 1 and x is 5. So this is the function, and if we want the area, that's going to be the integral from 1 to 5 of the function x e to the minus x. Okay, that's what it wants us to perform. So it doesn't say using algebra, but it does say with reference to A part 2. And what did we discover in A part 2? That this, right? We've discovered this. That the integral of x e to the minus x is this component. So because it's a definite integral, we're going to leap straight into that. We don't need c either because it's a definite integral. So what does it become? Minus e to the minus x. Take x e to the minus x from 1 to 5. All right, and then we're just applying the theorems of integration, right? Okay. Minus e to the minus 5, take away 5e to the minus 5. They're actually like terms, right? we've got one lot of e to the minus 5 and we're taking away 5 lots of it. So that's going to be minus 6e to the minus 5. And then we're going to have over here, they're like terms as well. We've got minus 1 lot of it, take another lot of it. We're going to have take negative 2 lots of e to the minus 1. Okay, so that collects to minus 2. We've still got the negative sitting here. And so how can we think about it? We can think about it like it's 2e take 6e to the minus 5. 2e to the minus 1, sorry. Or what does it look like another way? 2 on e takes 6 on e to the 5. Calculated it exactly. Part D. Refer to your overestimate calculations from Part B and your answer to Part C. Comment on the effect of increasing the number of rectangles used in your calculations has on the accuracy of your estimates. So maybe we will just quickly evaluate this. All right, so that we can discuss that in relation to the question. So we've got 2 on E. Take 6 on e to the 5. I've got 0.695. So let's look at how the estimate changed, right? We had 1.034, then we got 0.861, and the true value is 0.695. But you guys know where this is going, right? Increasing the number of rectangles. We went from 2 rectangles to 4 rectangles, increases the accuracy. It gets closer to the true estimate. So that's a comment that they're looking for there. Increasing the number of rectangles will increase the accuracy of the overestimate. And that's booklet 1. Okay. Clear a bit of space up here. All right, so booklet 2. First question. Let's have a read through of it. We've got concerns have been raised over the number of times per day that teenagers check their mobile device, such as a smartphone or a mobile phone. A study investigated the number of times per day that teenagers check their phone. A random sample of 100 teenagers was taken and the number of checks per day was recorded. The sample mean was found to be x bar equals 62.33 and the sample standard deviation was found to be s equals 19.31, which is assumed to be a good estimate of the population standard deviation. The histogram below shows the number of checks per day for this sample of 100 teenagers. All right, so we can see it's got quite a negative skew to it. With reference to the histogram above, explain why it may not be appropriate to use this sample to calculate a confidence interval for the population mean, the mean of X. Okay, we're looking at this histogram. Why is it not appropriate to use a confidence interval? And the answer is it's not normal. It's not even approximately normal. Okay, it's not normal. Therefore, confidence interval is not appropriate. Okay, you think about all confidence intervals require at least a normal approximation. Right? They need to be at least approximately bell-shaped. Okay. Suppose that many random samples of 100 teenagers were taken as part of the study and the sample mean X, capital X bar, for each of these samples was recorded. The histogram below shows the sample means. So here we have the distribution of X bar, the distribution of sample means. So they've made many observations. The central limit theorem applies when the sample size is sufficiently large, okay? Not n larger than 30, remember it has to just be sufficiently large. With reference to the histogram above, explain why in this case a sample of size of 100 is sufficiently large. Why? The histogram is approximately normal. It's roughly bell-shaped, so 100 is a good size to perform a normal approximation. All right, so just write something like, the histogram is approximately normal. Okay, using the sample of 100 teenagers considered in part A, calculate a 90% confidence interval for the population mean. All right, so we want to do a 90% confidence interval. And it's for a sample mean. So we're going test, interval, Z, and it's the first sample. And what are the options we're presented with when we do that again? We've got confidence level is 0.9. Okay. We've got a standard deviation of 19.31. We've got a mean of 62.33. And we've got a sample size of 100. All right, so calculate the 90% confidence interval. So if we evaluate that, now hang on, this is for the first sample, right? So let's be careful here. Calculate the 90% confidence interval for the population mean using the sample of 100 teenagers considered in part A. Okay, so because we're considering the sample in part A, not part B, so we're not considering X bar, the capital X, we're not considering the distribution of sample means, we're just going to use that information. Yep, so that's all correct. All right, so let's calculate that. 19.31, 62.33. So I've got between 59 and 65. Okay. Find the minimum sample size required in order to calculate a 90% confidence interval that has a width of no more than 5 checks per day. So we're going to be using this formula here. Okay, now I've drawn it up there for the 95% confidence interval because that's the one we're familiar with. The different component here is this 1.96. That's for 95% confidence. So really we've got this value of ZR from 2, right? For a 90% confidence interval. So I'm going to go through, refresh you guys on how to calculate that first. What does it mean to say 90% confidence? Maybe you'll have this one written on your cheat sheet, maybe you'll be able to work it out if you're confronted with it. But what it's saying is we have a Z distribution and we have an area of 90%, 0.9. All right? If we do that, what's the area of 0.9? We're saying, what are these values? Here's the -1, here's the +1. So how do you perform that? How do you do that calculation? It's an inverse normal calculation. Your tail is central. Your area is 0.9. And for a Z distribution, you have a standard deviation of 1 and a mean of 0. All right, so if you perform that inverse normal calculation, you get 1.645. All right, so we've got our value of Z alpha on 2, 1.645. We've got the standard deviation, 19.31. And the width of the sample is 5. We're saying a width of 5. All right, so between the upper boundary and the lower boundary, we have 5. And that's what we're going to perform. So we need to sample 161.4, and we need to round that to 162. Okay? Whenever we're calculating n, we round up to guarantee that level of confidence, right? All right, so any questions about that one? All right, so even my assumption would be when people have done this exam, some people would have had the 1.96 there, like they wouldn't have registered 90% confidence interval, but you'd still get 2, maybe even 3 marks for that. All right, let's move on. This is a nice question. This is a bit of a pearl of this one. So what are we at? Question 8. Consider the functions e to the negative x, x squared, and e to the negative x, x to the 3. The graphs of f of x and g of x are shown below for x is greater than 0. Each graph has 2 non-stationary points of inflection for x is greater than 0. On the graph, clearly mark the location of the 2 non-stationary points of inflection. So I'm going to bring it up. I'm going to talk about how we can do this. So you can roughly identify where they are. And I haven't seen the marking scheme for this exam. I might talk about marking schemes after we've done the trial exam. So I'm not sure how precise they want you to be with your answer. But the points of inflection, right, if we're thinking about g of x, where does it change from concave up to concave down? Somewhere along here, right? So, you know, you'd say probably roughly there and roughly here somewhere. All right, changes, they're the points of inflection. They where it changed shape. Concave up to concave down, and then concave down to back to concave up. So that's roughly where they change. But if we're unsure how precise they want us to be, we should be as precise as we can be. So what I've got is I've got the graph of g of x here. All right, that's what it looks like. And the points of inflection, okay, you can think about it 2 ways. You have these options in your calculator, right? You can graph the first derivative without having to calculate it, and you can graph the second derivative without having to calculate it as well. So, points of inflection on the function, they occur at the maximum and minimum points on the derivative. So this is a good refresher for us for calculus, right? So see how there's a maximum here? That corresponds with the point of inflection. They have the same x value. Similarly, the minimum on the green function corresponds with the other point of inflection. So on the function, the points of inflection will correspond with turning points on the derivative. And then lastly, they're going to correspond with the roots. Okay, the roots, root, maximum, point of inflection. Okay, roots on the second derivative, turning points on the first derivative, point of inflection on the function. Same over here, right? Root, turning point, point of inflection. So we can get those exact x values. So the first one is at, I should just look at my computer, 1.268, and the second one is at 4.732. So you just need to mark those points on the graph. And I would label them as well. I'd call them like P and Q or something like that. Okay. Points A and B are 2 non-stationary points of inflection on the graph of f of x. So now we're given the graph of f of x. Find the coordinates of point A. They want to know the coordinates this time. So that's where we're going to be doing a bit of calculator work. So how's the function different? E to the negative x, x squared. So I'll change that to a 2. And so the first point of inflection is A, and so that's going to occur when the second derivative. So if you want, you can unhighlight all of these, right? Here's my second derivative, here's the function. The second derivative has an x value of 0.586, okay? But we need the corresponding y value, right? So there's one value, but we need the coordinates, all right? So we're getting 2 marks there, 1 for each coordinate. So we've got 0.586 for the x. We need the y, so you're just going to do a g solve. When x is 0.586, what's the y value on the original function? 0.191. Okay, you could even express it exactly. You wouldn't have to g solve it. So another way you could write it, right? So we set it 0.586, and what's the function? The function is e to the negative 0.586. 0.586 squared. That would be an appropriate way to express it as well. That's the y component expressed exactly, right? Okay, so that's all for the first part there. Let's move on to the next part. This is where it gets a little bit hairy. So we've got, now consider the general function. We've got e to the negative x, x to the n, for x is greater than 0 and n is greater than 2. show that the second derivative, okay, read that carefully, show that h dash dash of x equals this. All right, so it wants us to find the second derivative and manipulate it until we get what they've got expressed there. So here's the function. Let's write up the function first and then we'll find the first derivative. h of x is e to the negative x, x to the n. We're getting a lot of marks in this exam for performing the product rule. We've done it heaps. So u is e to the negative x, u dash is negative e to the negative x. V is x to the n. And when you differentiate x to the n, you get n x to the n take 1. That's the power rule, right? That's just differentiation. Okay, smash them together to get the first derivative. U dash v plus u v dash okay, that's the first derivative. All right, for the second derivative, all right, you can see we would need to use the product rule there and there again. Now, there's no point doing this part again here because that is exactly the same function we started with. We know what that goes to when you differentiate. When you differentiate this component, you end up with this whole thing. So that means that this component, when you differentiate that component of it, what does it go to? We can just restate that part. It's going to go to minus e to the minus x, x to the n, plus e to the minus x, n x to the n. Okay, we know that from the first part. Let's see the link again. You differentiate this, that's what we performed here, you get this whole thing. We need to differentiate the first derivative again. We need to differentiate that whole thing. We know that that component, it's the same. So if that goes to this, then that component goes to, I've just written that whole thing again, but we've still got this other component that we need to consider.
What about the negative out the front of the...
Yeah, so I'll put the negative there, and we need brackets, don't we? Yeah. Very good. So there's a negative there, and so put brackets around it so that the negative distributes. Good pick up. Okay, so that's the first part. And then for the second part here, we're going to need to use the product rule again. So for the second component, we've got u dash, we've got v, and then v dash. Okay. N is just a number. All right. So when we differentiate it, this n is just going to hang out, and the power comes down. So it becomes n take 1, x to the power of n take 1, take 1. This is probably the hardest question in this exam. All right. So you bring the power down, and then take 1 from the power at the top. What does it simplify to? N take 1 is n take 2. All right, so we'll smash those those together, and we'll link it up with this part here. So we're going to have plus, when you differentiate this part, you've got u dash of v. So that's what that's going to be, minus e to the minus x, n x to the n take 1, plus n take 1, x to the n take 2, e to the negative x. It's pretty nasty. There's lots of things going on there. Worse. Okay, so now let's look along. We're going to try and collect a few terms, and then so we've differentiated it right, but now we need to show that it's what they've got. So we need to change it a bit. Okay, so let's look along. What can we collect along here? Firstly, that negative needs to distribute, right? So I'm going to have that term's going to become negative, and so is that term. Hang on, I didn't have the negative there, did I? Because that part's negative already. So that term's going to become positive, and that term becomes negative. Yep. Okay, so now looking along, these two, see that one and that one? They're actually like terms because they've got the same bases, they've got the same powers. We can bring those together. So that's the first thing we're going to do. So we've got e to the negative x, x to the n, and we've got two lots of this. Two lots of e to the negative x and x to the n take 1. And then we've got this other component at the end, n take 1, x to the n take 2, e to the negative x. Okay, now we can factorise the e to the negative x. I'm going to factorise it quite slowly just to really exhibit the what's going on here. E to the negative x is common. We've only got 3 terms now. We've broken it down. We've got 3 terms. And e to the negative x is common to all of them. So we'll pull that one out the front left and let's have a look at what we're left with. I shouldn't have that there. Take away 2. Alright, so we've pulled e to the x out the front. Now they've got it written as, the other factor they've got out the front is x to the n take 2. Now we can see that one there. We can see we've got x to the n take 2 there, but we can't see it on any of these. All right, we can't see it on these two. So we need to manipulate them somehow to pull x to the n take 2 out front. So here's how we're going to think about it. And you don't have to show this as a working out step. I'm just going to write up here so you can see clearly. X to the n, another way you could write it is x to the n take 2 times x squared. Okay, if you write it like that, x to the n take 2 times x squared, it's the same because they have the same base, they're multiplying one another. So if you add the powers together, you get x to the n. And now x to the n take 2 is a factor there. And similarly over here, all right, we've got the n there, we've got x to the n take 1. We can change that to n take 2 and multiply it by x, right? X by itself is x to the power of 1. If you add those together, add those two powers, you get the same power above. So that is how n take 2 is a factor. Now my assumption is, like, again, if you consider the marking scheme, by the time you get to this step, I don't think you need to show any of this as such. I think you can just go straight from there to the answer that they've got. Most of the marks are involved in the complex differentiation. So anyway, if we factorise the negative x to the n take 2, we've got x squared, we've got plus 2nx, and then we've got plus n take 1. QED. So we've shown that that's true. Okay. Hence show that the graph of h of x for x is larger than 0 always has 2 distinct points of inflection. So points of inflection are going to occur when the second derivative equals 0. Alright? So that means I'm going to make the whole statement e to the negative x, x to the n take 2. Okay? But both of these are powers, power functions. Well, this one is. So we've got e to the negative x and x to the n take 2 do not equal 0. Alright? So this component's clear why this does not equal 0. Exponentials don't equal 0. This one, because we're considering values of n greater than 2. Greater than or equal to 2. Alright? So then we're just considering this part. We're saying, when does this component equal 0? How do we show that this has 2 roots? Alright, now I think there's 2 ways to answer it. The first is, this is a quadratic, right? And so we're going to remember a couple of properties of quadratics. What you need to do is you need to find the roots of this quadratic. You need to show that there's 2 of them. So you're looking at that, you could try and factorize, it looks hard. Quadratic formula, just punch it out, okay? And that's what you can do. And that's going to give you the roots. If you need to show that it has 2 roots, then you would perform the discriminant, okay? So let's think about, let's have a quick lesson on both of those. So here's quadratic formula. And the inside component of the square root is the discriminant, okay? So we've touched on it a little bit this year, but mostly year 11. So if the discriminant is greater than 0, you have 2 roots. If the discriminant equals 0, all right, if that component is 0, you only have 1 root, and it touches at that point. And then if the discriminant is less than 0, that means that's a negative number, and there are no real roots. So to show that it has 2 real roots, you can show that the discriminant is positive. Okay, so let's just do that part first. If we evaluate the discriminant, it's going to be b squared, take 4ac. And in terms of this, we've got a is 1, we've got b is 2n, okay, the coefficient x, and c is n bracket n take 1. Okay, so we've got b squared, take 4ac. Not 2 squared. Take 4n squared, take 4n. I feel like I'm missing something.
Yeah, you're missing the N in the B.
In the B, thank you. That's an N, isn't it? B squared, 4n. Yeah, good. Has to cancel. Okay, good. So that's cancelled.
It's
And
4n
we're left with.
squared.
Say again?
The B is
Oh,
n squared.
that's
The
the
N.
squared component. So we're left with
Yeah.
that, are we? Why is it negative though? B squared take 4ac. This is negative here, isn't it?
No, I think it's meant to be positive down the bottom because of
Yeah, this component here is
Yeah.
negative, so B is negative, but that doesn't affect it. It's still
There's the
positive.
negative in the middle when you do the, because it goes to 4n squared and then it goes,
4n squared take 4n.
yeah, and then down to 1.
Oh yeah, and that negative distributes. Yeah, cheers. Yeah, good. Yeah, 4n. So we have a positive 4n. Okay, that's good. That's confirmed it. Okay, because now for any value of n that's positive, 4n is going to be positive. Okay, so if we have 4n, that's the discriminant. 4n, n is positive, so therefore 4 times a positive number also has to be positive. All right. So that confirms that there's 2 roots. But the other part we're required to show is that, so we've shown that it has 2 distinct points of inflection, but we need to show that it has 2 distinct points of inflection for x is greater than 0. All this tells us is that there's 2 points of inflection. So we need to satisfy the other component, and for that I think we need to use the quadratic formula to find the roots. All right, so we've already evaluated that component of it. So the quadratic formula then is just going to become minus b, now b is 2n, so minus b plus or minus this component here, all right, is 4n. That's what it evaluates to, doesn't it? Plus or minus the square root of 4n. And then on top of 2a is just on top of 2. And it can simplify a little bit, so I am going to simplify it. That's going to be minus 2n plus or minus 2 times the square root of n on top of 2. So minus n plus or minus square root of n.
The B should be minus 2n because it's
Yeah, negative. So that should be positive, shouldn't it? Negative b.
yeah in the question it's minus 2nx plus. So you've
That's
like
the-
where you've written it out.
Yeah, that needs to be
There.
negative.
Yeah.
Negative. So positive. N plus or minus root. Okay, and so what this shows you, all right, doesn't matter the size of n, okay, but n plus its square root is always going to be positive, and even n take its square root is also always going to be positive. Why? Because n is larger than its square root of n. So that's sufficient. You've shown that there's two roots, and this is where they occur, and they're positive. Okay, good. Let's move on to question 9 then. So that's a pretty tricky question, that one. Yeah, it's a pretty tricky question. All right, we've got some companies advertise their products by creating memes. They post these memes on social media in the hope that they'll be shared by a large number of social media users, thus promoting the product. Scientists studied the number of shares of memes for particular products called product C and found that the distribution depicted in the graph below, the distribution has a mean of 131.25 and standard deviation of 221. In an advertising campaign, companies may post a batch of memes on social media in the hope that some of these will be shared by a large number of users. Let Sn represent the sum of shares of a random sample of n products of C memes. There's a lot going on there, aren't you? Like, what's going on? All right, but the question's a bit simple. The two histograms below show the distributions for S10 and S75. Which one corresponds with S75? Okay. The second one, histogram B, and the reason is, as n increases, normality increases. There's another indicator as well, which is the mean of S75 is going to be 75 times the mean of X. So, 75 times 100, that's going to give you that sort of middle value there, whereas here they've only got 10 times 100, the mean is 1,000. All right, so histogram B, and you could give either of those tells. The faster one to write would just be as n increases, normality increases. Okay, part B. Show that the distribution of S75 has a mean of 9,844 and a standard deviation of 1914. So I'll put this in space. All right, so for S75, the mean of S75 is equal to 75 times the mean of X, which is 75 times, and what's our mean? 131, which equals, just taking a wild guess here, 9,844. The standard deviation of S75 is equal to the square root of 75 times the standard deviation of X. So that's going to be root 75 times 221, and we've got 1914. Okay, consider the distribution of Sn. As n becomes sufficiently large, what will the distribution of Sn tend towards? Normal distribution is the answer to part C, part 1. C, part 2, is n equals sufficiently large in this case? Explain your answer. So we're going to say yes, yes, because histogram B is approximately normal. Right, so that's C, part 1, C, part 2. All right, an advertising campaign is going to be successful when the combined total number of shares, the memes in the batch, is 10,000 or greater. It can be assumed that the memes in an advertising campaign can be considered a random sample. What is the probability that an advertising campaign consisting of 75 product C memes will be successful? So it's successful if it's larger than 10,000. That's what they've said. And they're saying, what's the probability of S75 being larger than 10,000? Okay, so this is the normal distribution calculation, right? We've got a mean, we've got a standard deviation, we've got a lower boundary. So it's NCD. Our lower boundary is 10,000. Our upper boundary is positive infinity. Standard deviation, mean. All right, so that's what we're going to calculate there. All right, so if we evaluate that, has anyone done that one?
0.468.
Thank you. Okay. A company would like their advertising campaign to have a probability of success that is greater than 0.8. All right, so they've only got here 46%, not very high. They want it to be 0.8 or larger. Show that this would be achieved by posting a batch of at least 90 product C memes. All right, so now we've gone from 75. 75 only gave us 46% success. So now they're saying show that S90. So that means we want the mean of S90, we want the standard deviation of S90, and we want to show that the probability of S90 being larger than 10,000 is larger than 0.8. That's what we're trying to show, right? And so we're just going to calculate the distribution of S90 and then perform that normal distribution calculation. So the mean of S90 is 90 times 131.25. The standard deviation of S90 is the square root of 90 times 221. All right, so we can evaluate those quickly. Here we've got 11, 8, 13, 8, 12.5. And then we've got square root 90 times 221. 2096. And so then our calculation is still lower boundary 10,000, upper boundary infinity. But we have a standard deviation of 2096 and a mean of 812.5. All right, and so if you perform that calculation, we'll probably get 0.801 or something like that. Has anyone done it? Yes, sir. So 10. And we've got 0.806. All right, so therefore it's true because the probability of S90 being larger than 10,000. Okay, so this is the last question. All right, so how are we going? We've been going for about an hour and 15, an hour and 20. So let's get this last one done. Okay, we've got at a sporting event attended by thousands of people, individuals spend time in a queue in order to enter the stadium. The probability that a randomly chosen individual spends time in the queue can be modelled by this probability density function, where t is measured in minutes, and it's shown below. So time on the x-axis, and it's a probability density function. So the area under the curve is going to tell you the probability of that event occurring. Calculate the probability that a randomly chosen individual spends between 0 and 10 minutes in the queue. So here's the graph, right? Between 0 and 10, that's this event. We need to calculate the probability of that occurring. So you can do it from the graph. You can go into your calculator, you can graph it, and GSolve, do the integral calculation, or in RunMat you can just put this in, can't you? Integral from 0 to 10 of 0.05 e to the minus 0.05 t with regards to t. All right, so I'll calculate that unless anyone else has. Seb's got it. Go on, Seb, spill. And I've got 0.393. All right, so what does that mean? It's the time spent in a queue, right? So between, probability of spending between 0 and 10 minutes is 0.393. 39% of people spend less than 10 minutes. Okay, on the graph, draw a representation of your answer. All right, so that means we're going to shade it. We're going to shade that region. Okay, that's how we represent area under the curve. All right, calculate the probability that a randomly chosen individual spends less than 60 minutes. All right, so now we're just changing the upper boundary to 60. Integral from 0 to 60 of 0.05 e to the minus 0.05 t. All right, and so if I'm doing that on my calculator, you know, rather than writing the whole thing out again, I'm just going to change the upper boundary. And you've got 95, 0.9502, which means there's still 5% of people that are spending spending more than 60 minutes in the queue. Oof. Alright, of 200 individuals who entered the stadium, how many does the model predict spent more than 60 minutes in the queue? Alright, so this is the probability of spending less than 60 minutes in the queue, which means the probability of spending more than 60 minutes in the queue is going to be 0.05, right, the inverse of it. So that's the probability of spending more than 60 minutes in the queue, and we have how many individuals? 200. 0.05 times 200, what are we going to get? 10. Alright. Okay, describe one limitation of using a function of the form a times e to the minus at. A times e to the minus at. Alright, so I might just sketch this on a graph to really demonstrate it, because there's no vertical translation here, that's the key. And so any graph of this form is going to look like this. Okay, so I'm trying to exaggerate the limitation here. It's asymptotic to the x-axis, all right, which means this probability is going to exceed 1, all right? You keep going along, and probabilities can't exceed 1. So what's the limitation of this function? It's asymptotic to the x-axis. Yeah, well, that's one. You can think of some others. All right. It is management policy that once inside the stadium, all individuals who spend time in the queue to buy food must be served within 20 minutes. All right, so they want them to get their food. They're not so worried about them getting in. The probability that an individual spends time in the food queue can be modelled by this probability density function. So we've got a new one where b is a positive value, t is measured in minutes, and now they've introduced a constraint for us, which is good. We've got a constraint, which means the limitation doesn't apply now. So we've got b times e to the minus 0.05t, and we know that the integral from 0 to 20 of this, for it to be valid, has to equal 1. Okay, for a valid probability density function, the area under the curve has to equal 1, and we're saying it has to occur over that interval, and now they want us to find the exact value of b. Okay, so we can integrate this straight away. B is just a number. In fact, you can pull b out front, so then you don't have to deal with it in the integral, right? E to the negative 0.05. All right, when you integrate that, it becomes 1 on top of negative 0.05, e to the negative 0.05 t, and you're going from 0 to 20. And so we're just going to evaluate this and solve it and make it look pretty. So we'll get 1 divided by negative 0.05. Is it 0.05 or 0.5? Yeah, 0.05. So is that 20? Yeah. So we've got negative 20 e to the negative 0.05 t from 0 to 20. And now we're just going to substitute in both of those components with the fundamental theorem of calculus. So we'll have minus 20 e to the minus 0.05 times 20. Take away minus 20 e to the minus to the 0. That's equal to 1. Alright, so that's 1. So we've got minus 20 e to the minus 1. And then here we've got plus 20. E to the 0 is 1. Okay, so I've just simplified that a bit there. E to the 0, that component's going to be 1. So then we have take negative 20 becomes plus 20. Here, 0.05 times 20 is negative 1. So that one's staying like that. And if we're solving for b, right, we're getting b by itself, we'll have b equals 1 on top of Yeah, 20 take 20 e to the minus 1. And there are ways of manipulating that, but that's perfect. You know, we've done enough. All right, here we go. On the axes on page 10, sketch the graph of g of t. So now that you've got this value of b, sketch the graph of g of t. So I'll bring both up. So 0.05 e to the power of point. Alright, so that's the first one. And then the second one is, no. Second one is 1 on top of 20 take. Right, so that's the value of b, and then we have multiplied by e to the negative 0.05. All right, and use the constraints that they've provided for us, so we can restrict our v window accordingly. So what have they given us? Between 0 and 60 for x. Particularly when you're dealing with probability density functions, because the y is going to be very low and 0.1 isn't. Beautiful. So they want you to sketch the green function. All right, you've got the blue function there, sketch the green one. All right, so helpful ways to get it, trace along it with F1. That's going to tell you some of the coordinates. So if you just plot a few coordinates and then draw a graph through those coordinates, that can be pretty helpful. Okay, last component is the probability of an individual spending between 0 and 10 minutes in the food queue greater than or less than the probability of an individual spending between 0 and 10 minutes in the entry queue. Give a reason for your answer without calculating the probability. All right, so if you were to calculate it, right, we don't have to, but if you were, all right, between 0 and 10 of the entry queue, that's going to tell you the probability of entering between 0 and 10 minutes. And between 0 and 10 of the food queue, that's going to tell you the probability of getting food within 10 minutes. Okay? So the question is, what's more likely? If you look at your graph and you go between 0 and 10, which one's going to have a larger area? The food queue, right? It's significantly higher. And so you get 2 marks. One is for answering, now let's just make sure, without calculating, is it more, what is it asking exactly? Is the probability, okay, it is greater in the food queue because the food queue, probability greater in the food queue because the food function, and how have they defined it? Is it g of t for food? We should use the same notation they've done. Oh, that's a bit confusing. Because g of t is greater than f of t between 0 and 10. Okay? Because the probability is higher over that interval, therefore the area under the curve is going to be higher over that interval. All right, so there we made our way through it, and we've done that in an hour and a half, really. So then you've got 30 minutes at the end, and that's even with me sort of stopping to explain to. There's ample time to get through it, right? And then you make sure you use the next 30 minutes to go over anything you're a bit uncertain of. All right, do you want to stop the recording there, I reckon?